Because adding potential confounding variables to our statistical model can help us to gain a deeper understanding of the relationship between variables, or lead us to rethink an association, it's important to learn about statistical tools that will allow us to examine multiple variables simultaneously. That is, look at more than 2 or 3 variables at the same time. The general purpose of multivariate modeling techniques, such as multiple regression and logistic regression, is to learn more about the relationship between several explanatory variables and one response variable.
These regression procedures are very widely used in research. In general, they allow us to ask and hopefully answer the question, what is the best predictor of, and does variable A or variable B confound the relationship between my explanatory variable of interest and my response variable?
For example, educational researchers might want to learn about the best predictors of success in high school. Sociologists may want to find out which of the multiple social indicators best predict whether or not a new immigrant group will adapt to their new country of residence. Biologists may want to find out which factors, such as temperature or barometric pressure or humidity, best predict caterpillar reproduction. So how can multivariate models help us to evaluate the presence or absence of confounding or lurking variables? Since the difficulty arises because of the lurking variable's values being tied in with those of the explanatory variable, one way to attempt to unravel the true nature of the relationship between explanatory and response variables is to separate out the effects of the lurking variable.
You may have already identified a significant relationship between your explanatory and response variables, and now want to think about whether this is a real relationship, or if instead the relationship is confounded by one or more lurking variables.
For example, here's a graphical association between birth order and number of cases of Down syndrome per 100,000 live births. As you can see, it looks like a linear association where the firstborn in a family has the lowest likelihood of having Down syndrome. With later birth order, up to a 5th born child, there's increased risk of being born with Down syndrome. This is a statistically significant association when analyzed via a chi-square test of independence, with birth order as the categorical explanatory variable and the presence or absence of Down syndrome as the 2-level categorical response variable. Another statistically significant relationship is the association between maternal age at a child's birth and the likelihood that the child will have Down syndrome. You can see here that babies of younger women, up to about the age of 29 or 30 to 34, have really low rates of Down syndrome. Among mothers aged 35 to 39 and older, you see the rates are clearly higher.
Remember, in the case of a confounding variable, the observed association with the response variable should be attributed to the confounder rather than the explanatory variable. We test for confounders by including these third variables, or 4th or 5th, in our statistical models that may explain the association of interest.
In these examples, it's possible that the association between a child's birth order and risk for Down syndrome could be confounded by maternal age. Alternately, the association between maternal age and Down syndrome might be confounded by birth order. Or, both birth order and maternal age might independently predict the likelihood of a diagnosis of Down syndrome after controlling for each other. Here's a graph that answers this question by showing that maternal age confounds the relationship between birth rank and Down syndrome, and that it's really maternal age rather than birth rank that's associated with Down syndrome. Here you see birth order along the horizontal axis. The maternal age groups are along the z-axis. Then on the y-axis, we have cases of Down syndrome per 100,000 live births. If we look across birth order separately for each maternal age group, we see that there really is no difference in rates of Down syndrome by birth order. In other words, once we control for the age of the mother, that is, examine the rates of Down syndrome across birth order, but one maternal age group at a time, there's no association between birth order and Down syndrome. If we look at rates of Down syndrome across maternal age for each individual birth order, we see an upward trend as maternal age increases. So if you look across these colors, this is a great graphical representation where we see that it isn't birth order that is associated with Down syndrome, it's maternal age. In other words, once we control for birth order, there's still an association between maternal age and Down syndrome. Birth order does not confound the relationship between maternal age and Down syndrome. The relationship holds even after controlling for birth order.